break? So I'm not quite sure if you really want to see your quizzes after spring break, but it's always time to move forward.
You run to work, it's pretty fast.
Okay, so this pile is for the 11 o'clock lab. And this is for the 2 o'clock lab.
What did we get?
Okay, so why don't we do a little reviewing of what we've covered so far in Chem 1B, since I hope none of you studied during spring break, because it's supposed to be spring break. Although I did hear rumors that there are some instructors who assign homework during spring break. Were any of you lucky enough to have homework during spring break?
I don't think so.
Okay, so anyway, as a review for Chem 1B, at the beginning we reviewed structure and bonding. So based on structure and bonding, compounds, we can figure out something about properties of that substance. So we applied this idea of structure and binding to organic compounds, and we can classify organic compounds by looking at functional groups. We know that different functional groups have different properties. So for example, we know that there are some functional groups which are non-polar, okay, so for example, the non-polar ones, I'm doing this backwards of how we introduced this way back at the beginning of the semester. So a non-polar functional group would be, these would be the hydrocarbons. And they include the alkanes and alkenes and alkynes. That's why, for example, oils and fats are insoluble in water. And then there are polar functional groups. And an example of a polar functional group would be the acids. So scientists and engineers can tailor or design substances which may be soluble in water or insoluble in water. So if you have a hydrocarbon which is insoluble in water, you can actually make this soluble in water by adding polar functional groups to it. So that's why these big biomolecules such as proteins are soluble in water, because they contain these polar functional groups. Okay, and then after that we talked about the solution process, so solution and solubility. So that solubility of a substance depends on the properties of that substance. In Chem 1A we said that a polar substance is soluble in another polar substance. That like dissolves like rule. But in Chem 1B we have to explain solubility in more detail, and we have to look at those chemical forces. So for example, in an ionic solution, what chemical forces are involved between an ionic compound and the solvent? Okay, so we looked at, for example, ionic versus molecular solutions. So the chemical force, which explains why an ionic compound is soluble in water, is the the lattice energy versus the hydration energy. Whereas with molecular solutions, we can explain why sugar is soluble in water, and the chemical forces in that case we need to look at are intermolecular forces. Now, more importantly, again, as scientists and engineers, you can tailor or design solutions. Or in other words, you can increase the boiling point or decrease the freezing point of a substance, and you can do that by looking at those colligative properties. So by adding a solute to a solvent, you can either increase the boiling point or decrease the boiling point. Yeah, so with boiling point elevation, freezing point depression, that equation is delta T equals I times K times M. And then the other colligative properties we looked at are osmotic pressure and vapor pressure lowering. Okay, so in other words, we can use these colligative properties to change the properties of a solution. And then after that, we looked at energy in chemical reactions. So we looked at reaction rates. And the rate of reaction depends on three factors. What are those three factors that determine how fast a reaction occurs? Yeah, so temperature and concentration and catalyst. So, and then we also talked about how a chemical reaction occurs. So a chemical reaction occurs when reactant atoms or molecules collide with sufficient energy for bonds to break or bonds to form. Okay, so when those collisions occur, temperature determines how fast those reactant molecules are moving. Concentration will determine the frequency at which those collisions occur, and then the catalyst, that does something to the mechanism of the reaction. And the catalyst will usually increase the rate of reaction. And then we looked at, in terms of the reaction rates, we can quantify these by looking at what we call the rate law. And then the rate law is based on looking at a rate constant. And this rate constant is determined by the activation energy of that substance. And then we drew pictures of these. So, for example, if we were to plot concentration on the y-axis, we'll call this concentration of reactants versus time. As the reaction occurs, what does this graph look like? Does it look like, so again, these are reactants. Does it look like this? No. Does it look like this? Look like that? No. Look like this? No. Let's put a zero. It looks like tic-tac-toe. So, yeah. So it looks like. So we just have a big mess there. And then we also looked at another graph in which we plotted energy versus the progress of reaction. And if we use a horizontal line, this represents the energy of the reactants, and then the second horizontal line represents the energy of the products. the difference in these two energies represents what quantity? Okay, delta H. So look at this difference here. That's delta H. Then to get from reactants to products, the reactants had to overcome some sort of energy. What was that energy called? Yeah, activation energy. So it had to go over that speed bump, and this energy here is the activation energy. So activation energy determines the rate of reaction. Delta H determines, actually partially determines whether that reaction occurs spontaneously or not spontaneously. And then after that we talked about chemical equilibrium. So it turns out that many reactions are equilibrium reactions. So whether it's an organic reaction or determining or describing solubility, for example, if we have NaCl solid, under certain conditions, that's an equilibrium with ions. So what are the conditions under which the NaCl solid is in equilibrium with its ions? What kind of solution is that called? Yeah, that's a saturated solution. So under these conditions, we have an equilibrium reaction. So in an equilibrium reaction, the reaction goes in the forward direction and the reverse direction. And then also at the beginning of the semester, we looked at this reaction. We reacted an acid plus an alcohol to make an ester plus water. Yeah, luckily in the lab that we did at the beginning of the semester, all those esters were for the most part pleasant smelling compounds, because there's some pretty bad smelling compounds we didn't smell. Anyway, this reaction is also an equilibrium reaction, so we can make this reaction go in the forward direction and make it go in the reverse direction. And again, as scientists and engineers, you can control the direction the reaction goes by applying some principle. What was the name of that principle? Yeah, Le Chatelier's principle. So by applying a stress, which means either adding a reaction or product or removing a reactant or product, you can make the reaction go in one direction or the other direction. And then we can quantify the amount of reactants or products in this equilibrium reaction by looking at it was a certain constant. Yeah, so that was the equilibrium constant. So we can quantify it by looking at this equilibrium constant for each reaction. And then we applied these equilibrium principles to acids and bases. So we looked at acid-base equilibria. So for acids, we have some generic acid HA. That's associating to H plus A minus. So the equilibrium constant for that was called Ka. And then if we have a base, A minus reacts with water, and the products of this reaction, this base hydrolysis reaction, is HA and HA and OH minus. And the equilibrium constant for this reaction is called Kb. And if we add these two reactions together, what do we get? Okay, so add those two together. And note that we have HA on the reactants here. HA is a product, so these cancel out. And then we have A minus cancels out. So what we're left with is H2O going to H plus OH minus. And we call this equilibrium constant the Kw. And how is Kw related to Ka and Kb?
Kb is Kw.
Yeah, or if we look at this, note that Kw is equal to Ka times Kb. And then we looked at another graph, another picture of how we can represent these acid and base reactions. So if you plot on the y-axis pH, and then the x-axis the volume of base added, this gives us a titration curve. So in our titration curve, we see all these different steps. And then based on this, we can figure out the pH at the halfway points, and then the pH at the endpoints. And then we have a formula to do that. So for example, at the halfway points, we know that pH is equal to the pKa. And then at the endpoints,